Alright, so this is going to be the video for section 3.5. In section 3.5, we're going to talk about the zeros of polynomial functions and also the fundamental theorem of algebra. The rational zeros theorem tells us that if a polynomial function written in descending order of the exponents has integer coefficients, then any rational zero must be of the form plus or minus p divided by q, where p are factors of the constant term and q is a factor of the leading coefficient. So this is one that we're going to apply a lot in this section. We're also going to see a little bit of the fundamental theorem of fundamental theorem of algebra, where every polynomial function of degree n being greater than or equal to 1 has at least one complex zero. And here, this is probably one that's already familiar to you. Numbers of zeros. It says that every polynomial can have no more zeros than its degree. So what we're going to do is we're going to go through these next couple of examples, and I'm going to keep referring back to these right here so we can get a little bit of a better grasp of these definitions. But let's look at question number 1. It says, use the rational zeros theorem to determine the potential zeros of this polynomial. So what we're going to do here, and if we look back to the rational zeros theorem, it simply just says that any rational zero must be of this form. So what we're going to first do is we're going to find potential zeros. Now, we're about to find a whole lot of things. I'm not going to say that all of these are necessarily zeros. They're just potential zeros. So what we need to do is we first need to identify whether or not this polynomial has integer coefficients. So if we look right here, the coefficients are just going to be the numbers that are in front of each one of our x terms. And if we look at all of these things, these are in fact all integers, right? They're either 1, 2, 3, 4 or negative 1, 2, 3, 4. So those things are integers. So now we know that since they're all integers, we can apply the rational zeros theorem because it tells us that if these things have integer coefficients, now we can apply this thing. What we need to focus on now is the factors of the constant term. So let me write right here that this is going to be our constant term. And our constant term in this polynomial is simply just that thing that doesn't have an x attached to it. So here our constant term is equal to negative 10. Now let's try to figure out what the factors are for negative 10. Well, the factors of negative 10, we're going to designate those to be p. So the factors of negative 10 are either plus or minus 1, plus or minus 2, plus or minus 5, or plus or minus 10. Right? You can take positive 10 and multiply it to a negative 1, and that's going to give you a negative 10. You can take a negative 5 and multiply it to a positive 2, and that's also going to give you negative 10. So these right here, plus or minus these numbers, are going to be the factors of our constant term. The next thing that we need to look at, we're going to show that q, these are going to be factors of our leading coefficient. So let's take a look at q. So first off, our leading coefficient, the leading coefficient is going to be the number that's attached to the x with the highest exponent. Well, here our highest exponent is 4, so therefore our leading coefficient is going to be the number that's in front of that, and that is also the number 4. So now we need to identify what q is, and q is going to be the factors of the number 4. Well, the factors of the number 4 are again plus or minus 1, plus or minus 2, or plus or minus 4. So these things are our factors of our constant term and the factors of our leading coefficient. Now what we're going to do is we're going to list all possible zeros. So now these are going to be potential zeros. Potential zeros. And our potential zeros are simply just going to be plus or minus p divided by q. So therefore, if we take this p right here to be our numerator and take q to be our denominator, we're simply just going to go down the list. So I'm going to start off with this one right here for p. So it's going to be plus or minus 1 divided by q, right? That's what we're going to list as our potential zeros. So our first one for q is simply just 1. Now so I did this one right here. My denominator was this one right here. Now what I'm going to do is I finished this one. So now I'm going to go on to this one as being my numerator. So we have, again, plus or minus 2 divided by 1. Now I'm going to use this one as being my numerator, plus or minus 5 divided by 1. And then lastly, the last one is plus or minus 10 divided by 1. So now I went through this entire list for p's, but I only use this q right now as my denominator. So now I need to go through the list of p's again and just use the second value that I have for q as my denominator. So I'm going to start it over with the p's. I'm going to have 1 over 2 now. Then plus or minus 2 over 2. Plus or minus 5 over 2. And plus or minus 10 over 2. So now I just went through it, and you can see it right here. If you compare the numerators, 1, 2, 5, and 10, here we have 1, 2, 5, and 10. So the only thing that I've really switched from this first line to the second line are just the denominators, which we've now used 1 and 2. So in order to finish up our potential zeros, we have to use all of these again as our numerator, but now we're going to have 4 in our denominator. So we have plus or minus 1 divided by 4, plus or minus 2 divided by 4, plus or minus 5 divided by 4, and plus or minus 10 divided by 4. So now these numbers, these 3 rows right here, these are all of our potential zeros. Now, let me say a couple things about these potential zeros. They're just potential zeros. I'm not saying that all of these things are zeros. That's the first thing. The second thing is we can definitely simplify this stuff, right? I think everybody is good to go with the fact that plus or minus 1 divided by 1 is just the same thing as plus or minus 1. And plus or minus 2 divided by 1 is just the same thing as plus or minus 2. So I can definitely simplify these things. But let's also look here in the second row. Here we also have plus or minus 2 divided by 2. Well, 2 divided by 2 is still just 1. So this right here is the same thing as just saying plus or minus 1. So we're definitely going to have some things that are redundant as well after we simplify. So the 3 things is this. These are potential zeros. We can most certainly simplify this stuff over here. And yes, some of this stuff over here is definitely going to be redundant, right? This is just one example of it being redundant, these 2 numbers right here. But then if you look over here too, this is 5, and 10 divided by 2 is also just 5. So now these 2 things over here are redundant. And we can keep going through stuff, right? Like there's a bunch of other ones that are redundant, 2 divided by 4 and 1/2. But I just want to point out the fact that these things are redundant. But they're also going to definitely list all of our potential zeros. If you go through that process that we just went through, you're definitely going to be able to list all of the potential zeros. We're not going to simplify this stuff and clean this stuff up, but you should be able to do that on your own. The next thing that we're going to do is we're going to use this to completely factor this polynomial right here. And we're going to factor it in order to find all of our solutions. So let's think about that here for a second. If I came to you and I said, how do you factor this polynomial? Your first response is probably, I have no idea, right? Because this is a long polynomial. We could make it even longer, right? We could have an x to the power 4, x to the power 5, and just keep on making it longer and longer and longer. But if somebody came to you and goes, hey, can we factor this thing? Well, just looking at it, like we're not 100% sure how to factor it. But one of the things that we can do is we can use what we did here above to find all of our potential zeros. So let's go ahead and do that again. Again, we're going to look at the constant term. Here, our constant term is simply just that thing that doesn't have an x with it. So here our constant term is 35. And we're going to look at the factors of 35, and the factors of 35 is what we're going to call p. So our factors of 35 are simply just, again, plus or minus 1, plus or minus 5, plus or minus 7, and plus or minus 35. These are all of our factors of the constant term 35. Next thing that we need to do is we need to look at our leading coefficient. And our leading coefficient is simply just the number that's associated with the highest power. Here the highest power is 3. So therefore the coefficient that goes along with this term is just 1. Now the factors of our leading coefficients, what we're going to call Q, well, this one happens to be really, really easy. What are the factors of the number 1? It's just plus or minus 1. So therefore, if we go through this again, we try to figure out the potential zeros, all of our potential zeros. We're again just going to go down the list and take these things as being our numerator, and now we just have one possible option for our denominator. So therefore, we're going to have plus or minus 1 divided by 1, plus or minus 5 divided by 1, plus or minus 7 divided by 1, and plus or minus 35 divided by 1. So I'm trying to be really, really, really explicit about exactly how we find our potential zeros. But again, I just go through all of these and use them as my numerators. And then I would go through all of my possible Q values and use those as my denominators, but here I just have one Q value. Now this one's really, really easy to clean up, because again, we just have plus or minus 1, plus or minus 5, plus or minus 7, and plus or minus 35. All right. So let me stop here and say this, right? One of the things that I haven't pointed out yet from the previous example is, how many numbers do I have right here in this row? Well, I have plus 1, and I also have minus 1. I have plus 5, and I also have minus 5. Plus 7 and minus 7, plus 35 and minus 35. So therefore here, I don't just have 4 numbers, but since I have the plus and the minus of all of these, here in this row, I really have 8 numbers. So let's think about that here for a second. I'm saying that these are just potential zeros. Again, I know I'm repeating myself, but these are just potential zeros. I'm not saying that each one of these things are zeros, right? Now, how do I know that each one of these things aren't zeros? Well, let's go back up here to our number of zeros theorem. Our number of zeros theorem says that every polynomial can have no more zeros than its degree. Have no more zeros than its degree. So if we come down here and we look at the degree of our polynomial, the degree of our polynomial is the highest exponent on our variable. So therefore, the degree of this polynomial, this is degree 3. Degree 3, because that's our highest exponent. So therefore, if we have a degree 3 polynomial, then we're going to have no more zeros than we have degree. So therefore, we're going to have at most 3 zeros. But here we're identifying 8 potential zeros. So we know that 5 of these numbers in here at least are bogus, right? So you can kind of think about it like this. What are we doing down here, really? If I came to you and I said, hey, what are the zeros of this polynomial? You would say, I have no idea what the zeros of the polynomial are. I just have no idea. So technically speaking, you're saying, hey, it can be anywhere from negative infinity to positive infinity. I really don't know how to narrow it down. Well, we've just taken the all possible numbers that could potentially be zeros, and we've narrowed that down to a set of 8 numbers, which is shrinking down the set of potential zeros from potentially infinity all the way just down to 8 numbers. So we're shrinking it by a lot. Now, we're not quite there yet because we only have 3 real candidates for zeros in here, but that's what we're doing with this first step. All right. So now we've basically just done what we did up here in the previous problem, but the previous problem asked us to just identify potential zeros. Here we're actually trying to find the solutions, right? So we're not just trying to find the potential zeros. we're actually trying to figure out of these 8 numbers, which 3 of them are actually zeros of this polynomial, or actually solutions of it. So here's where a little bit of guess and check comes into play. And this is the part about it that kind of sucks, right? But what you want to do now is you want to say, okay, I have 8 potential numbers. Let me start off with just one of them, plug it in, and based off of what we learned last class, is if you plug in a number and it comes out to 0, well then you know the number that you just plugged in is a 0 of this polynomial, right? That's what we learned from the remainder theorem. If we plug in a number for x, and all of this does not come out to 0, well that's our remainder, so therefore that number is not a 0. So let's do it. Let's say that I randomly just choose, I'm just going to simply just randomly select, so I'm going to say that I'm randomly select the number 1. If I randomly select the number 1, then right here we have plus or minus 1, so I'm just picking the plus 1. If I take this 1 and I plug it in, we're going to get 1 cubed plus 13 times 1 squared plus 47 times 1 plus 35. Well, if you just look at this, I have a bunch of numbers and I'm adding them all together. Well, this certainly does not equal 0. So therefore, because it does not equal 0, we know that positive 1 is definitely not one of our solutions that we can use. So now what we would do is, again, I'm going to say that I'm randomly selecting, I'm going to now randomly select the number negative 1. So now let's plug in the number negative 1. If I take negative 1 to the power of 3, right, all of this to the power of 3, plus 13 times negative 1 squared, plus 47 times negative 1, plus 35, well, let's do it. Here, this is going to come out to negative 1. This is going to come out to 13, right, because negative 1 squared is just positive 1 times 13 is just, you guys can't see that, it's just 13. Now I have negative 1 times 47, so negative 1 times 47 is just negative 47, and here I still have plus 35. Well, now if you add these things together, now this does in fact equal 0. So what we've just done now is we've identified that negative 1 is one of the zeros of our polynomial. So therefore, we just found out that negative 1 is one of our solutions. So now I'm going to set that one aside, right? I'm going to say one of our solutions, get a little bit of extra room up here. One of our solutions, I'll have them over here, I'll have like a running tally. One of our solutions we know is x is equal to negative 1. X is equal to negative 1. So now the question is how do we find the other solutions? Well, we could literally just continue on with that process, right? So then I wouldn't change it. I wouldn't say that I'm randomly selecting it. I would then just do positive 5 and negative 5, just like we did positive 1 and negative 1, and then plus or minus 7 and plus or minus 35. And eventually we would just come out with 3 numbers that would work. But what we can also do now is this. We know that x is equal to negative 1 is a solution, so therefore we also know that one of the factors is x plus 1. Right? If x minus 1 is a solution, then a factor has to be x plus 1. So what we can do now is, this is what we did last class, we could take our polynomial, and I'm just copying down our polynomial so I don't have to keep moving the papers around and stuff. We could take this polynomial and we can divide it by this factor because we know that we're going to get a remainder of 0. So let's go ahead and do this. There's a couple of different ways that we can do it, but I think consensus showed last class that a lot of people prefer a synthetic division. So let's go ahead and do synthetic division. If we do synthetic division, then our coefficients are going to be 1, 13, 47, and 35. I don't skip any terms in here, right? So I don't have a 0 down here. And over here, since this is a positive 1 over here, I'm going to write a negative 1. This is our setup to synthetic division. What we did last class was we pulled this 1 down. then negative 1 times 1 is equal to negative 1. Now we can add 13 minus 1 is equal to 12. Negative 1 times 12 is negative 12. 47 minus 12 is equal to 35. And then negative 1 times 35 is negative 35. So voila, like we said, we're going to have no remainder. Now you're probably wondering, well, how the heck does this help us? Well, what we now know is that if we want to write this again, we would have this as being our remainder. This is going to become our constant term. This is going to become our x term. And this is going to become our x squared term. Right? So here I have 1, 12, and 35, just like I have 1, 12, and 35 right here. Well, now if we look at this, now the question becomes is, we already identified one factor of this polynomial. Now, can we identify the factors of this polynomial? We're looking for two numbers that add to 12 but multiply to 35. Two numbers that add to 12 but multiply to 35. Well, those two numbers are 5 and 7. So therefore, we can factor this as x plus 5 and x plus 7. And if we do that, now we factored this. So therefore, what that means then is if these two things are factored to this polynomial, and this right here is also a factor of our original polynomial, then we can say that x cubed plus 13x squared plus 47x plus 35 is the same thing as x plus 1, which is one of our factors, x plus 5, which is a factor up here, and x plus 7. So now we just found the factors to our polynomial, which means that our zeros, or our solutions, are just negative 1, negative 5, and negative 7. Negative 1, negative 5, and negative 7. And if you look at these three factors right here, and you compare them to the list that we had up here before, negative 1, negative 5, and negative 7 are definitely in that list of potential zeros. But now we've just narrowed it down to only 3 zeros, which we had from our number of zeros there. All right, so that's number 1 and number 2. Let's move on to number 3. Number 3. Number 3 is asking us to do exactly what we just got done doing in number 2. We're asked to completely factor this polynomial and to find all of the possible solutions. So first off, since each one of our coefficients is an integer, we know that we can apply the rational zeros theorem. So what we're going to do is we're going to look at our constant term. Our constant term is 5. So therefore here P is going to be plus or minus 1 and plus or minus 5. Now here for our leading coefficient, our leading coefficient here is the number 6, since it's the coefficient that's associated with the highest degree. So therefore Q is going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So just like we did before for our potential zeros, we're going to start off with these as being our numerators, and this one right here is our denominator. So we're going to have plus or minus 1 divided by 1. Then we're going to have plus or minus 5 divided by 1. Now we went through these two right here along with this as being our denominator. Next thing that we're going to do is we're going to do plus or minus 1 divided by 2. And plus or minus 5 divided by 2. So now we've taken care of these two as being our denominator. Next thing that we're going to do is we're going to do plus or minus 1 divided by 3. And plus or minus 5 divided by 3. And again plus or minus 1 divided by 6. And plus or minus 1 divided by 5 divided by 6. Alright, so again I just went through here and I identified the potential zeros. Again here, let's see, can we simplify some of this stuff? we definitely have 1, 5, 1/2, 2.5. So I don't see anything that we can simplify from here. Well, obviously, except for the fact that we can call this a 1 and this is a 5. But other than that, there's no redundancy in any of these. So again, like we would do before, we would simply just start off with guess and check. We would say, okay, take positive 1/3, plug it in right here, see if that's equal to 0. If it's not equal to 0, then we know that that's not a 0 of this polynomial. Then we would go on to negative 1/3, plug it in, see if it's equal to 0. So I'm going to spare you guys some of that arithmetic on this. If we go through here and we use negative 1/2, so if we select that x is equal to negative 1/2 and we plug this into here, then we're going to see that that in fact is equal to 0. Not only for negative 1/2 does it work, but it's also going to work for 1/3. Now here, the next thing that we can also find out is that if you plug these two things in and then you try to factor it, what we're also going to see here is that zeros of this polynomial are also going to be plus or minus the square root of 5. Now hold on a second here. Here it just says that if we go back to our rational zeros theorem, it says if a polynomial function written in descending order of exponents has integer coefficients, then any rational zero must be of this form. But a rational zero, what it means for it to be a rational zero, is simply something that you can write as P over Q. So since it's P over Q, right, a rational is just the same thing as a fraction. Any zero that you can write as a fraction, we can write as this. Well, here, the square root of 5 you cannot write as a fraction. So therefore, that's why this plus or minus square root of 5 is a 0 to this polynomial, but is not given in this list right here. Any number that we can write as a fraction is going to be over here. Any one of these zeros that we cannot write as a fraction is not going to be contained in this list. All right. So if you go through here and plug these things in, both of these will give you 0. Then you're going to end up with a quadratic, and if you solve that quadratic, you get plus or minus 5. All right. Let's take a look at number 4. Find a third degree polynomial that has zeros 3, 6, and 1. 3, 6, and negative 1, I'm sorry. So the way that we're going to do this here is this. We're trying to find a third degree polynomial that has the zeros 3, 6, and negative 1. Let's think about that. If I want to have the zeros of 3, 6, and 1, that means I can plug in 3 and it's going to be equal to 0. I can plug in 6 and it's going to be equal to 0. Or I can plug in negative 1 and it's going to be equal to 0. So therefore, what we can have is we can have x minus 3, right? Because here if I plug in 3, now this is going to be equal to 0. So whatever I multiply 0 by is always going to be equal to 0. I can have x minus 6, right? If I plug in 6 in right here, this is going to be equal to 0. So that means that all of this is going to be equal to 0. And here I'll have x plus 1. So again, if I plug in negative 1 right here, then this is going to be equal to 0. So all of it's going to be equal to 0. So this right here is a polynomial that has these three things as zeros. Now, the only other thing that we have to do is make sure that it's a polynomial of degree 3. So that means that the highest exponent that we're going to have is going to be to the power of 3. Well, since we have these three terms, and each one of these terms just has an x in it, we know that this right here is a third degree polynomial. If you if you distribute these things out, you'll find out that this comes out to x cubed minus 8x squared plus 9x plus 18. Now I'll let you go through the steps of factoring that stuff out, but after we do this right here, we'll see, or I said factoring it out again, just expanding this out, you'll see that the highest exponent is 3, so therefore this is a third degree polynomial. Alright, the next pages after this are the practice problems, and those are left for you. So this then concludes the video for section 3.5.